We picked as a topic for our term project random number generator used for frequency hopping. The article that we found to base this off of is entitled "A Secure Frequency Hopping Synthesizer for Reconfigurable Wireless Radios." It is by Aaron Kumar. Frequency hopping is used for many wireless communications. I'm going to read a spot here. In the introduction, frequency hopping is one of the spread spectrum communication techniques in which the transmitting frequency will change periodically. Frequency hopping is widely used in military radios because of its highly secure and anti-jamming properties. And this paper uses the Blum-Blum-Shub generator to choose which frequency to use. So as you can see in this table, there's a pseudorandom number generator that randomly chooses a frequency out of this frequency table, and then that frequency is used by the device that's transmitting. So to get into the actual algorithm that is used, it relies on two prime numbers, P and Q, which are called Blum prime numbers. Those are multiplied together to get N, which is called the Blum integer. And the way that you get the next random number in the series is you square the previous one and then take mod n. This is a stream generator, so you can get a continuous number of bits. So to get the next bit, it requires the next random number, and then you take the least significant bit of that random number to get your next bit in the stream.
As Joe said, we implemented Blum-Blum-Shub. It's a fairly simple implementation. Currently, this is set to use that rather long number, M or N, in the documentation, and then we have to seed these with a beginning number. We'll start with something. So this is our first number that it comes up with in the random number generator. If you use the least significant bit, which is what we went over in class, as you could see here, you get only the first. You get the first number, or you get 1. Currently, it's also showing a frequency matching first decimal bit, or first decimal number, as well as the first decimal number. That way, we can actually have a variation in frequencies showing up. The cool thing about this particular use of a pseudorandom number generator is if we can use the exact same program on both of them, as long as we have the same C number, we should get the same numbers for the matching. So no matter how far I go down, if I go all the way to 100 right there, I'll go all the way to 100 on this one. The 100th frequency will still match. This implementation is a fairly simple one. As you can see, there is occasionally some repeating frequencies. Right here, there's 2 repeating frequencies. In a normal implementation for this, it would have a much larger frequency range with more than just 10 frequencies it's using. So that way it creates even more randomness and a farther spread, so it's harder to follow where the message, what frequency the message is coming across in. Along with that, if I stop this one and I restart it and I give it a different seed, that's nothing like the first one, I'm not going to get the same pattern of numbers. So if I go all the way to 100 here, none of them are going to match. Well, some of them are going to match, but not enough to really begin getting the message in. That way, when, say, 2 different military operations are using the same system, as long as they're using different seeds between them, they can use the same frequency range and shouldn't overlap too much. Going into the implementation, so here it's a fairly simple implementation. As Joe said, we have our Blum primes, which is P and Q. I picked 2 4-digit prime numbers, trying to go nice and big, and then M right here is our Blum integer, and that's allowing us to stay within a a certain, or with to use the algorithm. Simply enough, all it does is it just loops through doing it each time, squaring the number, and then modding it. That's what this pow mod function right here does. Attempting to do large numbers for the power with mods overflows here in C++. So I created a function to do it using long longs, as well as if the power is some really large number, it still has the capability of running it simply through a procedural method instead of a strictly math one. So as you can see here, and then it just pulls the frequency that matches that last significant decimal digit out of our table right here. The table we have here isn't really large. We only get 0 through 9 here, but in a real implementation of this, you'd be having quite a large frequency with probably hundreds of types of frequency or hundreds of frequencies you could use, allowing it to continuously get stay different. That way, no one can follow it or jam the signal or anything with still having proper transmission. All my power modding function does is it simply multiplies some of them while modding, so it kind of goes through procedurally, multiplies a couple of them, mods it, and it continues through that, keeping it smaller than the full size of the data type.
Now, to touch on some of the practical matters of using frequency hopping and using the BBS to support it, I can expand on what Joe was saying. The reason why the military uses frequency hopping is because it's highly resistant to radio jamming. Typically, radio jamming will affect only a narrow band of the entire spectrum, and by using frequency hopping, we can avoid that band. We'll only see little breakups in our conversations. It's also difficult to intercept as we're jumping between different frequencies. Our adversaries cannot listen into our calls, into our radio communications, because we're jumping between frequencies. They'll get little blurps and ifs, because as this thing is changing about 10 times a minute, from what I understand. So, and as Cody spoke to, many different radio communications can be happening on the same spectrum, because as they use different seeds to seed their conversations, they're jumping to different frequencies at different times. Now, this doesn't increase the bandwidth of our normal conversations. Logically, each conversation is still using one band at a time, so you still have the same bandwidth on any spectrum, but it does allow for all the different conversations to be obscure. One of the reasons we picked this article that deals with frequency hopping is because of my background in the military. When I first joined, I was a forward observer, and what they would do is they would sit on the front of the hill and they would call for fire for artillery assets. Artillery assets, they cannot see where they're landing their shots. So a forward observer would sit on the front of the hill and tell them where the enemy's at and how much they missed by. For this to work, the forward observer needs to be able to share their position and the target and the enemy's positions to higher headquarters to fire artillery. You can see how, if the adversary were to pick up this information, how that would affect our soldiers in the battlefield. They would know where we're at. They would know that we know that we're where they're at as well. So this will not only cost lives, but also cost missions. In conclusion, this BBS is one of the most secure ways to do this. Different papers speak on this, and our paper spoke to it as well, and that's why they used it to create this frequency hopping simulation. It's hard to backtrack and recreate these lists without using the seed itself. The military relies on this for their mission's sake and for the soldiers' lives' sake, as we do a lot of very secure communications over these channels. We'd like to thank you for your time. I hope you enjoyed the presentation.